A system that moves among 64 voxel states needs a rule for choosing the next state, but that rule must stay exact, directional, and stable, instead of behaving like an ordinary floating point softmax. The main idea is to replace exponential probabilities with a rational geometric normalizer, so the chain can make sparse transition choices while preserving its parity checks and its built-in torsional pump. The explanation begins with what a transition kernel is, then builds the hyperbolic score, the sparse normalization step, and the directional valve that creates a net current. The chain can be treated as a collection of states connected by allowed moves, where each row of the transition kernel lists the probabilities of moving from one current state to its possible next states. For the 64 voxel cube, the kernel does not need to store every possible jump equally because each state mainly interacts with nearby oriented channels that represent directions through the cube. A normal softmax would turn scores into probabilities by using the exponential function, but exponentials usually create irrational or floating point values that can differ slightly from machine to machine. In a deterministic protocol, even a tiny low-bit disagreement can break a parity check, so the transition rule must use exact rational operations whenever the on-chain state is updated. The geometric score is built from a Torsional state, which has one scalar part called W and three vector parts that describe position or motion through the lattice. To compare two states without square roots, the design uses a Lorentz-style inner product, where the scalar parts multiply positively and the vector parts multiply with a minus sign. Hyperbolic quadrants is the squared Lorentz comparison -1, so it acts like a distance-like measure while staying polynomial and rational when the quaternion coordinates are rational. A nearby compatible neighbor receives a better score because the logit is the negative of the hyperbolic quadrants, meaning smaller quadrants becomes a larger chance of transition. The score also includes a torsional resistance term, which makes moving with the preferred chiral winding cheaper than moving against it. This resistance turns a plain geometric comparison into a directed rule because the score from state I to state J is not necessarily the same as the score from state J back to state I. After the rational scores are made, sparse max replaces ordinary softmax by projecting the score list onto the probability simplex, which is the set of non-negative probabilities that add to one. For rational scores, sparse max finds a rational cutoff and keeps only the scores above that cutoff, so some neighbors get exact positive probabilities and the rest become exactly zero. This sparsity matches the idea of geometric collapse because the chain chooses a finite local support instead of spreading a small amount of probability across every possible state. The scalar part W also controls the effective curvature or temperature of the normalizer, which changes how sharply the transition row concentrates around the best scoring neighbors. If W drives the temperature too high, the row becomes too uniform, and if W drives it too low, the row collapses too hard onto a single choice. The stable design keeps U in a middle range, so ties and contradictions can be softened without turning the whole rule into either flat noise or a brittle argmax. The directed resistance breaks detailed balance, which is the condition where every flow along an edge is exactly cancelled by the reverse flow. When detailed balance is broken in a consistent chiral direction, the Markov chain can have a positive net current, meaning probability circulation advances through the torsional loop instead of merely sloshing back and forth. The final kernel is therefore row stochastic, rational on the executable skeleton, sparse over the local channels, stabilized by the quaternion scalar, and asymmetric enough to drive the intended pump. Irrational quantities can still be used for off-chain analysis or visualization, but any residual error is quarantined outside the 64-state rational skeleton, so the deterministic parity rule remains valid. The result is a hyperbolic softmax in purpose rather than in name only. It scores with rational hyperbolic quadrants, normalizes with sparse max, stabilizes with W, and uses chirality to produce a directed Markov current.